All right, guys, hard 9 o'clock start. We're 9:10 now, 10 seconds past 9, so we'll begin. Thank you all for RSVPing, for those that did, really appreciate that. So it's good just so that we can print the exams. So I've just got a list here of things we'll chat about before we get started. So firstly, why 2014? So the reason I've chosen this exam is this is part of the old math studies course, and what I've managed to do is get rid of the studies questions that are irrelevant, and then there's a couple of key concepts that I always want to highlight each year, and so they pop up in this exam. I think this is a good one. The other reason is it allows you to access yourself independently, the more recent exams. So this exam comes up to 95 marks. So your exam that you'll sit is 2 hours and 10 minutes, is 100 marks. So it's pretty close, and so we'll work through it. I reckon it'll take us about an hour and a half, and so the purpose of, that's good because it'll demonstrate to you you can get those 100 marks done in an hour and a half, and then you'll have a bit of time at the end to answer or to go back and check some of your answers and so forth. So we should be able to work through it pretty quickly. So what our plan is to work through this together. So if you haven't got an exam and you've come in late, there's exams next to Gemma. So after this, if you want anything printed, please hang around. So when we finish, I'll dismiss everyone. You're welcome to hang around and I can print some stuff. We don't have any more A3 paper though, so everything I will print will be A4, just double-sided and stapled at the top left. And as we're working through, please feel free to interrupt me if you think I've done something wrong, okay, which frequently occurs. Or if you have a question about what we're doing, or if there's something you haven't misunderstood, please feel free to stop, interrupt. I don't want to rush through it. We want to make sure we're working at an appropriate pace where everyone's on board. I'll be referring to the textbook throughout, probably not frequently, but sometimes I'll pull the textbook out, as well as our notes books, right? So our calculus notes books and our integration notes books. There might be things we highlight in there. Most of my calculations I'll do on my calculator here. For graphing, my preference is to use Desmos just because it's much easier to type things into Desmos. But if people want, I can bring up the calculator emulator. I think that's probably everything. So let's begin. So let's open up to the first page, and page 1, all right, you can expect, this has been the case for the past 20 years of exams, is they always have differentiation, simple differentiation. Occasionally they'll put an integration on there, but these are what you call easy marks. In an exam, there's always easy marks to get and hard marks to get, and so your goal, make sure you get the easy marks. So question 1, everyone should get full marks, all right? Make sure you understand how to differentiate. So question 1A here, we have simple differentiation, and like we said when we're doing the calculus test, read it, find dy and dx for the following functions. There is no need to simplify, okay? So that means you can just express, for example, this one, we could express it as 5 times 3x squared, we could express it as 15x to the 3. Doesn't matter, you'll get full marks either way. And then we have takeaway 4, the derivative of 7 is 0. So that's a perfectly suitable way to express our answer. You won't be penalised if you wrote it as 15x to the power of 3. Now, for a number of these, I'm going to solve them. I'm going to really draw out and explain to you how we're solving them, but you don't need to put this, a lot of the time you won't need to put this level of detail in. So for instance here, first, what we have to do here is apply the chain rule. So I want to express this as a function to the power of n, right? So that's 100 plus x squared to the power of a half. Okay, so that's an example of a step that you don't need to include, all right? All I'm doing is stating it as a function to the power of n. And we're very clear, this is still the same function, and now because it's a function to the power of n, we can differentiate it. So our notation changes to dy on dx, and that's going to be half times 100 plus x squared. So we have n, f of x, n take 1, okay, the chain rule, and then multiplied by the derivative of the inside. So when we have a function to the power of n, f of x, n take 1, f dash of x. Now, I was thinking about notation, all right, y is not equal to that, rather dy on dx is equal to that. So when you're going back through the exam and you're checking your work once you've finished it, that's an important thing to keep an eye out for. Have I done my dy's on the x's? Have I put plus c's on my integrals? So question 1, it's a bit short here, but normally there's sort of a product rule in there as well, sometimes a quotient rule, and it tends to be about 5 or 6 marks, but make sure you get those easy marks in question 1. Very good. Let's turn the page. Okay, let's have a read. Consider the function f of x is 5, take 10 on top of x. The graph is shown below. Point A naught is where x is 2, and point B is where x is 6. They're also shown joined by the chord A naught B. So a chord is just a line joining 2 coordinates. Part A, determine the slope of this chord. So we're asked here to determine the slope of a line. So I'll scroll through to the exam and I'll point out a few things on the board up here. So the first, we need the coordinates of A naught, and we can see that pretty clearly. We've got x is 2 and y is 0. So that's our first coordinate. So I'm just going to list the coordinates, right? I said we'll do this in a sort of drawn out manner. We can see the x value is 2, the y value is 0. And for point B, we know the x value is 6. We know the x value is 6, but we don't know the y value. However, we do know the function. The function is 5, take 10 on top of x. All right, so if we want to know what's the y value when x is 6, we're going to put x is 6 into here, 5 take 10 on 6, and that's something you can evaluate on your calculator, and in an exam situation I'll probably encourage you to. You want to outsource as much of your mental exertion as you need to, as you have to, so you're sort of saving yourself. So 5 take 10 on 6, and we've got 10 on 3, and now we're just finding slope. Okay, so slope of the chord is y2 take y1 on x2 take x1. So we have 10 on 3 take 0 on top of 6 take 2. All right, so what we have is we have 10 on 3 on top of 4. 4 by itself is on top of 1. A on B on C on D simplifies to AD on BC. So that's 10 on 12 or 5 on 6. And again, using your calculator there to support you. So the slope of chord A naught through to B is 5 on 6. Okay, the slope of the chord approximates the tangent at x is 6. So let's just have I'm going to have to sketch it anyway to refer to it. So it's sort of going like this. And so they're saying the slope of this chord roughly describes the slope here. Okay, that's what they're saying. The slope of this chord roughly describes, it's an approximation of the slope here. At point A1, the slope of chord A1B better approximates the slope of the tangent to the curve at x is 6. On the graph, draw a possible chord A1B. So here we have A naught and B, and all we're asked to do is draw a new chord that is closer in slope to this chord here, okay, to this tangent here. So that's going to be anywhere to the right of A naught, and you draw a chord. You can see that the slope of this new line, so I'm going to call that point A1, the slope of this new line, all right, is closer to the slope of this line than the initial chord is. So 1 mark there for that. All we have to do is draw it, draw a possible chord. Excellent. Okay, now here's a first principles question. Now first principles questions don't occur in every exam, but they're relatively common enough to make sure we recap them. So using first principles, find the slope of the tangent to the curve at x equals 6. So we have the function 5 take 10 on top of x, and we're going to use first principles to find the slope. So first principles formula, f dash of x is the limit as h approaches 0 of, now we'll write it out like this, 1 on h multiplied by f of x plus h, take away f of x. So all I've done there is state the formula for first principles. So just grab an exam next to Gemma and grab a seat. All right, I've printed the perfect amount. How good is that? Unless anyone else rocks up. Toby Cole. Okay, so we've got the formula, let's shove it in. So, limit as h approaches 0, 1 on h remains out the front. Now f of x plus h, all we're doing is restating this with x plus h everywhere there is an x. Okay, so that's f of x plus h. And then take away f of x, so then we just plug the original function back in here. Okay, again, please stop me at any stage if you have any questions. All right, so looking at this, we're going to simplify it straight away because we have 5, take away 5. So the 5s are going to cancel, we can get rid of them. And let's just restate what we've got and distribute some negatives as we go forward. So we're going to have the limit as h approaches 0. And if you prefer, you can swap the terms around. It doesn't matter. That order remains the same, right? The equality remains the same. Now what we want to do is we want to cross multiply the denominators. Now at this point, it's good to assign the negative somewhere. I'm just going to assign it to the numerator. It doesn't matter where it goes. It doesn't belong to both the denominator and the numerator. It belongs to the whole thing. So let's just assign it to the top and we'll cross multiply the denominators. So what we're going to end up with is we'll have minus 10 multiplied by x, so I'm moving that denominator up here. And then we have plus 10 multiplied by this denominator, x plus h. And then that's over the top of the two denominators multiplied together. So all we've done there is cross multiply the denominators. Okay, now we're going to expand the top and collect like terms at the top. Never expand the denominator. Okay, in first principles, it will all come out in the wash. So all we're going to do is we have minus 10x plus 10x plus 10h at the top. So again, I'm doing this in a drawn out manner. I'm doing it over a number of steps. And so first principles, all right, this is, again, I would say an example of an easy mark question where it's just so methodical, right? You just follow the steps. What do? Here's the formula, sub in, all right, simplify, collect like terms. That's what we're up to now, collecting like terms. So minus 10x and plus 10x will cancel. Okay, collect like terms, cancel h, all right? And so the way you know you're on the right track, once you've collected like terms, that's a checkpoint, right? Where everything in the numerator has to have a h in it in order for h to cancel. Now, we've only got one term in the numerator, 10h, and so we can see we've got 10h at the top, h at the bottom, h will cancel. So I'll come up here to show you what we've got left. We've got the limit as h approaches 0 of 10 on top of x times x plus h. Now, as h approaches 0, so now we can apply the limit, we've got 10 on top of x squared. So we have f dash of x is 10 on top of x squared. Now, this is where it pays to read the question as well, okay? Because often with first principles, you just take it to the derivative function. However, we're asked here to find the slope when x is 6 using first principles. So we've used first principles and now we need to find f dash of 6. All right, so plug that in and we'll have 10 on 6 squared. So let's have 10 on 36, 5 on 18. Any representation like that is fine, okay? So 4 marks there, 5 marks, you want to make sure you get those. And I'll just say, with first principles questions, when you're finding the slope, remember there's a number of ways we can use our calculator to find this. So firstly, if you were to graph this function on your calculator and trace along it, it can tell you the slope at x is 6. And the second way is we can do it in RunMath. We can type in what's the derivative of this function when x is 6. Okay, we can type that in as well. So I won't go over those now. If you want to flag that, you can write it down. How do I do that? Okay, question 3. We have a company produces marbles. Now with stats questions, there's a temptation to speed read it because why waste your time reading? But I think it's better to read it slowly and thoroughly than to rush through it and miss something important, make a mistake, and then have to correct it. Okay, so use your time, read through it slowly and carefully. The company produces marbles. As a result of the process used, the weight of the marbles in grams can be modelled by a normal distribution with a standard deviation of 1.1. The mean weight is unknown. To investigate the mean weight, the company randomly samples marbles and weighs them. Each sample taken contains 100 marbles. Sample 1 has a mean weight, so this is the mean of the sample, of 5.72. Find a 95% confidence interval for the mean weight of marbles based on this sample. So always, we want to just go straight to our calculator here. You don't want to have to type all that, write all that out on the formula, try to do it manually. We'll just go straight to our calculator. So we're doing a confidence interval for a mean. All right, so just to recap those calculator steps, we're in stat mode, interval Z first sample. Okay, so our syntax, our confidence level is 95%. The standard deviation is 1.1. Our observed mean is 5.72. And the number of trials is 100. There are 100 marbles in each sample. So we're just typing that in and evaluating. Okay, and then we'll state we've got 5.504 and 5.935. So I'm going to always write four figures and then round to 3. So this rounds to 5.50 and this rounds to 5.94. Now, just on notation and how examiners, like how we mark this when we're marking exams, you get 1 mark here for the correct boundaries and you get another mark for correct notation. Okay, so when we say correct notation, what we mean is for a sample, you have to have mu in the middle. All right, heaps of students having marked exams before, they put X bar in the middle. Okay, that's not correct notation when making an estimate about the population mean. And the other thing people do is they use less than rather than less than or equal to. Okay, so we pick on both. You need less than or equal to, and you need mean. You get 1 mark for correct notation, even if your boundaries are way off. All right, so that's how we answer question 1, 2 marks there. Part B, on the diagram below, draw the confidence interval for sample 1 from part A. So we have a number line. I might try to draw it on my screen actually. And we're asked to draw a confidence interval for sample 1. So sample 1 goes from 5.5, so that's going to be its starting point. I'm just going to put some dots on it for you. Alright, so we go from 5.5 to, and then we have 5.94. So here's 5.9, so 5.94 is going to be about there. So you should be drawing a confidence interval over that region. Alright, so 1 mark there just for illustrating it. Part C. Is it possible for mu, that is the mean weight of the marbles, to lie within all 3 confidence intervals? Give a reason for your answer. So, 1 mark here, we're going to write no, it's not possible for the mean to lie in all 3. Now the reason it's not possible is because sample 2 and sample 3 do not overlap. So that if the true mean lies between sample 2 and sample 3, they won't overlap. Now, when you're answering a question, when you're asked to justify something, it doesn't pay to just write heaps of words. Often you find, again, having marked exams, students end up contradicting themselves. So reflect on what you're going to write. Don't start writing straight away. Often this can be something that you use scribble paper for. You know, it's like when you do a draft and you write something down and then you perfect it and you perfect it and you make it better and better and better. And so then what you state on your exam is your final claim. All right, so what we're going to say, we're saying 2 things. We're saying we're answering the question. Answer the question. No, It's not, the mean can't lie in all three. And then just say sample 2 and 3 do not overlap. And that's sufficient. All right? So, nice and easy. We're not writing a paragraph of text trying to justify it. We're just being short, sharp, and shiny, concise. Okay. After further investigation, it is determined that the mean weight of the marbles is 5.73 grams. Does this mean there was a flaw in the way in which sample 2 was taken? Give reason for your answer. So they find the mean is 5.73, so that's going to be like here, right? And so that lies in sample 1 and sample 3, but it doesn't lie in sample 2. So they're saying, is something wrong with sample 2? So again, we're going to answer this in two ways. We're going to say, not necessarily, because what a confidence interval means, I'm going to write it up here and then I'll describe it to you. Not necessarily. 95% of confidence intervals will contain the true mean, which means 5% won't. Okay, so that's what a confidence interval is, right? When we say 95% confidence, what it means is if we do 100 confidence intervals, 95 of them will contain the true mean and 5 of them won't. Okay? So it's not, doesn't mean there's something necessarily wrong with sample 2. It's possible that it is this circumstance where it won't contain the true mean. All right, and again, it's only a level of confidence, so it's not a guarantee. All right, confidence intervals don't make any guarantees. Okay, question 4. All right, so have a read. The displacement of a particle in meters to the right of origin can be modelled by the function s of t, where t is measured in seconds. The stationary points of this function at t equals 1, t equals 4, and t equals 9. The inflection points of the function are at t equals 2, t equals 4, and t equals 7.6. All right, so I'm going to do a rough sketch of this as well so I can refer to it. Might make that a little bit less flat. There we go. Pretty happy with that. Okay. The velocity of the particle can be modelled by the function v of t, and the acceleration can be modelled by the function a of t. Complete the sign diagrams below. All right, so up here we have these points, right? So we have a local max, we have a point of inflection, so this is t is 1. We have a point of inflection at t is 2. We have a local minimum here, like a non-stationary inflection, sorry, at t is 4. Then we have another point of inflection at 7.6 and a local minimum at 9. Okay, so let's draw the v of t sign diagram first. Now, v of t is the derivative of s of t, and so all v of t shows you is when is s of t increasing and when is s of t decreasing. So what we can see is we're increasing until we get to 1. All right, we have positive velocity. The displacement is increasing, it's getting further away, so we have positive velocity until we get to t is 1. Then we're decreasing until we get to t is 4. Okay, the velocity is decreasing until it gets to t is 4. Then it's decreasing again. Okay, so we have that stationary point of inflection. Decreasing until we get to t is 9, so displacement is decreasing, the displacement's getting closer to 0. And then after t is 9, the displacement is increasing. All right, so we get 2 marks there for putting that on the sign diagram. So again, all we're doing for v of t is the slope of s of t. We're just saying when is the slope positive and when is the slope negative. So a nice 2 marks there to get. Okay, then for a of t. And the other way to answer this, right, is the roots on v of t are always stationary points. Okay, so we can see slope is stationary here, here, and here. So they're the roots. All right, now on to a of t. Now, the roots on a of t, they're the points of inflection. All right, and we're told where the points of inflection are. So a of t is the second derivative. So we have points of inflection at 2, 4, and 7.6. And I'm just trying to match up the scale with what I've got above. Okay, so that's the first thing we can do, is we can just plot the points of inflection, all right? So on the second derivative, all right, so this is s dash dash of t. On the second derivative, you will have the points of inflection. On the first derivative, you will have the stationary points, all right? So where the slope's stationary, where it changes shape. And so we can observe that as well. Concave down until we get to 2. Concave up until we get to 4. Concave down until 7.6, and then concave up, okay? Having that, bowl opening upwards, bowl downwards, bowl upwards, bowl downwards, so concavity. So then the way we answer when's it positive and negative is if a function is concave down, the second derivative is negative, okay? It's concave down until we get to 2, concave up until we get to 4, concave down, concave up. All right. Okay, hence or otherwise, sketch a graph of v of t. So we're going to use these two sign diagrams to sketch a graph of v of t. So here's going to be our graph of v of t, and we need numbers from 1 through to 9. 10, 15, 5, 6, 7, 8, 9, 10. Okay, now for v of t, 10, okay, so if we're going to draw a graph of v of t, here are the roots. It's got a root at 1, a root at 4. So straight away, let's go through and mark the roots there. We've got a root at 1, a root at 4, and then a root at 9. Now, the reason we're not given a scale on the y-axis is because we don't know how far dilated it is that way. That's irrelevant. What we're interested in is its general shape. So next what we'll do, let's mark the points of inflection. So one thing I want to point out, points of inflection on f of x correspond with the turning points on f dash of x, which are the roots on f dash dash of x. So that means our points of inflection on our original function are going to be the turning points on our derivative function. And even then, you can think about it like, if this is the original function, this describes the slope of the original function, okay? So if we think, if we're decreasing until we get to 2 and then increasing, that means we would have a local minimum at x is 2. All right, so we have a local minimum at x is 2. We're decreasing. And the reason I know the local minimum occurs below the x-axis is because v of t is negative when x is 2. All right, so let's have a look at what's going on with v of t. All right, we're above the x-axis, and then we transition to below the x-axis. And we're below the x-axis until we get to 4. And then we're still below the x-axis, okay? It's 0 at that point, but it touches the x-axis and comes back down. And then we have another local minimum, okay? So we're decreasing until we get to 7.6. Now again, so that's x is 7.6 or t is 7.6. And then it crosses at 9. So the dilation isn't important. We don't know what this y value is. We don't know how far down it goes, but we do know, all right, we do know local minimum at t is 2, local max at t is 4, local min at t is 7.6, and then we know the roots are at 1, 4, and 9. Okay, is everyone okay with that one? Excellent, okay. Let's answer the last part then. Describe how the velocity of the particle changes between t is 7 and t is 8. Okay, describe how the particle of the velocity changes. All right, the velocity of the particle changes. So we're interested in how does the velocity change? Acceleration describes the change of velocity. And so let's break it down. I might answer up here so everyone can see. Let's break it down. Now we're asked between 7 and 8 seconds. So let's talk about when t is 7, what's going on with the velocity. All right, when t is 7, that's about here, we can see we have negative velocity. So in the context of the problem, we're moving to the left, moving left. And what else is happening with acceleration? We have an acceleration of the acceleration is negative when t is 7. So that means it's accelerating to the left. Okay. Then something changes when time is 7.6. Okay? So when time is 7.6, if we look at our sign diagram here, it still has negative velocity, so it's still moving left. All right? But it's not accelerating. It's not accelerating. This is the acceleration function, and we have a root on the acceleration function when time is 7.6. So it's moving left, but it's not accelerating. It's moving at a constant speed. All right, and then we have when t is 8, it's moving left, but it has positive acceleration. So if it has positive acceleration but moving left, what that means is it's slowing down as it moves to the left. Slowing down, decelerating to the left. All right. There we go. All right. Any questions about that one? So yes, Brie?
Could you just do a relationship between like slowing down and speeding up with velocity and acceleration functions?
So what's the link between when something's slowing down? Yep. So okay, so it's going to be slowing down when its velocity and acceleration have opposite signs.
Yep.
Yep. And it's going to be speeding up when they have the same sign. Yep. So yeah. So if you think slowing down, like if you have positive acceleration but negative velocity, they're contradicting one another. Whereas if they're the same, if you've got velocity in the negative direction and accelerating, then you're speeding up in the negative direction. Yeah. So yeah, if they have opposite signs, then it's slowing down. If they have the same sign, then it's speeding up. Very good. Okay, question 5. Good question. All right, we have consider the function 2x ln x. The graph is shown below. An overestimate for the area of the region between the graph and the x-axis from x is 1 to x is 5 is to be calculated using 2 rectangles of equal width. On the graph, draw the rectangles used to obtain this overestimate. Okay, so make sure, like easy marks, right? When you're drawing rectangles on a graph. Okay, so here's what the graph looks like. It goes below and then above, and we have from x is 1, 2, 3, 4, 5. Now we want an estimate from x is 1 to x is 5 using 2 rectangles. Okay, so we're dividing from 1 to 5 up into 2 rectangles, and they are both overestimates, so we're drawing them above the curve. Now make sure you draw the whole rectangle. There we go. Calculate this overestimate, giving your answer correct to 3 significant figures. So 2 marks here, 1 for getting the correct answer, and 1 for the answer and 1 for rounding correctly. So let's have a look. So we want the area of this rectangle, all right? Now the function is 2x ln x, that's the function. So that's going to help us find the y value. So that means this rectangle here, I might break it down into rectangles, has a width of 2, so we have 2 multiplied by its height, and its height is the y value when x is 3. So when x is 3, we have 2 times 3 times ln of 3. So we have 6 ln 3. So that's its height, that's the width of the rectangle, okay? So the first rectangle has an area of 12 ln 3, and the second rectangle has a width of 2, and its height is going to be 2 times 5, so 2 times 5, ln of 5. All right, 10 ln of 5, so that becomes 10, 20 ln of 5. So that means our estimate, the sum, we can use this kind of notation, the sum of each rectangle is, and we're not required to show any working here, we're just required for an answer, but it's 12 ln 3 plus 20 ln 5, and this is one we're going to type into our calculator. We get to 4 figures, and then we will round. So earlier I got 45.37, So this kind of thing now is where they pick on significant figures, all right? So having marked exams, they're not too fussy about significant figures elsewhere. Like, we encourage you follow the rules, right to 3/16, but when they state round to 2 decimal places, round to 3 significant figures, that's when you have to do it. That's when we're assessing it, all right? So we're not picking on you everywhere you don't do it. We're picking on you generally in one particular spot. So I've stated 4 figures here. My 4th figure rounds up. So we get 45.4. And it's an estimate of area. So we'll put units, 45.4 units squared. All right, very good. So 2 marks there, 1 mark for drawing the rectangle. All right. Now, here we are. There's some good question here. Find dy on dx if the function is x squared ln x. All right, so we want to find the derivative of this function. We're going to use the product rule. We have u multiplied by v. So u is x squared, u dash is 2x, v is ln of x, and v dash is 1 on top of x. All right, so we'll smash all those parts together. U dash v plus u v dash plus x squared dy on dx. So make sure we're using correct notation, dy on dx. Now, having marked exams, like, you don't have to list u and v, but I encourage you to do it. For me, it helps me sort of order those things properly. So we've got those there. All right, now this term we can simplify, right? X squared times 1 on x, that's just going to simplify to x. All right, we have 2 lots of x squared at the top, x at the bottom, simplifies to x. Excellent. Okay, find dy and dx, done. Part 2, hence, okay. You never do anything in vain. Anytime you see hence, that means using what you've just done. So we have to use this somehow. Hence, find the integral of 2, show that the integral of 2x ln x is this, okay? So they want us to find this integral. They want us to show that this is true. So what we're going to do then is we have to use what we've just done. And so what we've done is differentiation, right? We know if I have this function and I differentiate it, this is what I end up with. Therefore, I can make an integral statement. The derivative of this is this. Therefore, the integral of this, okay, so this is from part CI, the integral of 2x ln x plus x is x squared ln x. Okay, again, this is from chapter like 4E in the textbook, where we're doing integration by differentiation. We're going, differentiate this is what we get. Therefore, if we integrate this function, this is what we get. Okay, so first we make an integral statement, and we're interested in this part. So we're going to split the integral, right? That's a property of integrals we can do. We're going to split that to be 2x ln x plus the integral of x. Now make sure you're writing your dx's. And now it's just a matter of solving through for 2x ln x. So I'm going to subtract this term from both sides of the equation. So we will have 2x ln x Alright, so all I've done there is move it over to the other side. And then the integral of x is just x squared on 2 plus c, which is exactly what they ask us to have. They've stated it as half x squared, but you're absolutely fine in stating it like that. Okay, so that's good. All right, so again, alone, you're not expected to know how to integrate something like that, 2x ln x, okay? But sometimes they will put them in by getting you to differentiate first and making a link. It's very common, making a link between differentiation and integration, okay? Cool, last one. Using your result given in C part 2, all right? So even if you haven't been able to answer C part 2, you can still answer this question. Find the exact value of the area of the region between the graph f of x and the x-axis from x is 1 to x is 5. Okay, so they want the exact area under the curve from x is 1 to x is 5. That's going to be area from 1 to 5 of 2x ln x with regards to x. That's what we're asked to calculate exactly. So it's not enough just to type it into your calculator and evaluate to 3 significant figures. We're even told, give your answer in the form a ln b plus c. So, using your result, okay? So using this, all right? So we don't know how to integrate that. You're not expected to know how to do that, but because we've made the link, we've now got a relationship that we can use. So this becomes x squared ln x, take x squared on 2 from 1 to 5. Okay, so we can perform the integral because we know it's true from the process of differentiation. So, and now we're just applying the fundamental theory of calculus. We don't need plus c because it's a definite integral. Plug in the numbers. So we're going to have 5 squared ln 5, take 5 squared on 2, take, and then we have 1 squared ln 1, take 1 on 2. Now we're just going to simplify. Ln of 1 is 0. That's going to just disappear. Ln of 1 is always 0. Even then, you can check on your calculator. It won't really collect with anything here, but I guess that's something we should know. So we've got 25 ln 5, and then we've got here take away 25 on 2, and then we have take negative, so that becomes plus a half. And so we'll just simplify this a bit. Minus 25 on 2 plus a half, that's minus 24 on 2. All right, again, I'm doing it in the draw it out manner, aren't we? 25 ln 5, take 20, and 24 divided by 2 is just 12. Now, here's a place where you can confirm you're correct. So right now what I will do is move on, but then when I'm finished the exam, I'm finished early, I'll come back and check that this is the correct answer. And the way we can do that is you can type this into your calculator, all right, and evaluate it to 3 significant figures. And you can type this into your calculator and you can verify that they are the same. That's a way of confirming that you're correct. Okay, so there'll be a few more that pop up where we can confirm that we're correct throughout. Like this next question. Okay, question 6. Consider the function minus 7 on top of root x, where x is positive. The graph is shown below. So we have a function below the x-axis, looks like this, and we have area from 1 to 4. Okay. Write down an expression for the area of the shaded region shown on the graph. Okay, so it's a little bit tricky here because the function is minus 7 on top of square root of x. Now what we should know is that if we want to know area below the x-axis, it has to be the negative of the function, all right? It's 0, take away the function. Our top function is y is 0, take the area. So what it should be is minus 7 on root x, okay? Which simplifies to 7 on root x. All right? So have to make sure that that's positive because area is a positive measurement. Okay, evaluate the expression. All right, so all you're doing is typing that into your calculator. You can do it on the graph mode if you want to, g-solving that area. So for part A, we get 7 on root x. For part 2, we get 14. Okay, part B. Consider the integral from 1 to a of the function minus 7 on top of the square root of x, and that's equal to minus 30. And we're told a is larger than 1. Find the exact value of a. So all we're doing here is processing this integral and trying to solve it for a. All right, so what we'll do first is we want to integrate this. We have minus 7 on top of the square root of x. So straight away, what I'm going to do is we express that as x to the power of n. So at the moment it's x to the half. We take it to the top, it becomes x to the minus half. And I'm going to pull the minus 7 out the front of the integral. And don't forget your dx's, don't be lazy. Alright, so we've done two things. We pulled the minus 7 out the front and we raised the x to the top. So now it's ready for us to integrate. Now what we can do here as well is let's divide both sides by minus 7. So we can even shove that minus 7 over here, so we're not even considering it. Remember, we're trying to solve through for a, so we want to simplify the left-hand side as much as we can. So let's do this in 2 steps. So over on the right-hand side, we'll divide it by minus 7. So we have minus 30 divided by minus 7, so the negatives will cancel. Now in here we have the integral of x to the minus half. So we're just applying the x to the n integral law. That's x to the minus half plus 1, which is positive half, on top of minus half plus 1, which is also positive half from 1 to a. Okay, so here this will simplify to 2 root x. And over this side we have 30 on 7. And now we're just applying the fundamental theorem of calculus. All right, so when we divide by half, just multiplying by 2. X to the half is square root of x. So what have we got? We've got 2 root a, take 2 root 1 equals 30 on 7. Okay, solving through for a, so what we'll do next is 2 root 1 is just 2, so we're going to add 2 to both sides. Now again, this is something that you can perform on your calculator, but 30 on 7 plus 2, that'll be 44 on 7. Then we divide both sides by 2. Can people see? Sorry. So we'll have root a is 44 on 14. And then to get a by itself, we're going to square both sides. So a is 44 on 14 squared. Okay, so this is another one where we can check if we've got the correct value. And the way we would do that is we take this number and we plug it in there. And we evaluate it and see, does it equal minus 30? Okay, so another one where we can check our answer. We've found an exact value. And you'll find to express it like this, I mean, that will simplify a little bit, right? Well, that'd be 22 on 7 squared and 484 on 49. But that like that is absolutely fine. Very good. Okay, on to question 7. Now this is quite a tricky question. So we said there's easy marks to get, there's hard marks to get. These are some of the harder marks to get, especially some of the later parts in this one. So make sure you get the easy marks and then we just try get the hard marks. All right, so let's read it carefully as well. A company produces photovoltaic solar panels that generate electricity when exposed to sunlight. These solar panels are made up of cells, and the amount of electricity generated by a solar panel is the sum of the electricity generated by its cells. The company produces a solar panel containing 30 cells. The cells are randomly allocated to solar panels during the production process. Of the cells used to produce solar panels, 9% proved to be defective. Defective cells generate no electricity. Non-defective cells generate 4 watts of electricity when exposed to sunlight. So different people have different strategies. They might go through and they start like highlighting where the numbers pop out. That can be useful. Okay, if you find that useful, feel free to do that. We're going to be using all of those numbers that popped up at some stage. Okay, so the first question is, what is the probability that a 30-cell solar panel will contain no defective cells? So what's going on here is we have 30 trials and we want to have none fail. We want no failures, 0 failures, and the probability of a failure, the probability of it being defective, not P hat, just P, is 9% or 0.09. All right, so that's sort of the information that we've pulled out of it. Now there are 3 ways to answer this. I reckon the most effective way is just if BPD, all right, I want 0 failures out of 30 trials, xn, and then the probability of a failure is 0.09. All right, so that's what we're evaluating. That's probably the easiest way to do it. A couple of other ways you can think about it is this one, P to the K, and then what's it, Q to the N take K. Okay, we can use the binomial distribution formula. Or you can even think, if I have 0 failures, that means I have 30 working cells. And so what that means is the probability of a cell working to the power of 30. All right, so all 3 of these processes will generate the same answer, but we get 2 marks there, and I got 0.05905. Okay, 4 figures, and then round to 3. 0.591. All right, how many defective cells can a 30-cell solar panel contain if it is to generate at least 100 watts of electricity when exposed to sunlight? Okay, so we want at least 100 watts of electricity, and we know that each cell gives us 4 watts of electricity. So if we go 100 divided by 4, that means 25 cells. We need at least 25 cells to be working. Okay, at least 25. If we had 24 cells working, well, it would only generate 95 watts of electricity. We want at least 100 watts of electricity. 100 watts of electricity, each one generating 4 watts. That means we need at least 25 cells. So for part B, 1. So if we have, now let's answer this. So it's split into 2 parts. I'm getting ahead of myself. If it's to generate, we're just asked how many defective cells can it have? So we need 25 working cells, which means the most defective cells it can have is 5. All right, because there's 30 in a solar panel, we've got 25 that are working, which means the most we can have that are defective is 5. Okay, part 2. What is the probability that a randomly chosen 30-cell solar panel will generate at least 100 watts of electricity? So it's saying, what's the probability of having at least 25 working, or at most 5 failing? All right, so I think 2 ways to think about this. We want 25 successes out of 30 trials, at least 25 successes out of 30 trials. So we have lower boundary, upper boundary. So how do we do this? BCE, between 25 and 30, out of 30, and the probability of it working is 0.91. Okay, so if it's got a 9% chance of failure, 0.09 of failing, then the probability of it working is 0.09. So what this calculation is this is the calculation of a randomly selected solar panel having between 25 and 30 working solar cells out of 30. Okay, so we can evaluate that. Or you can think about it as the most we can have failing, we can have between 0 and 5 failing out of 30, and the probability of failure is 0.09. Both of those calculations will generate the same solution. All right, and so when we evaluate that, we get 0.9519, which is 0.952. All right, so maybe those marks, they're tricky marks, especially like considering the 100 watts and so forth and evaluating that part. But this is probably where it gets really tricky. All right, the company is designing a solar panel that will be labelled as generating 220 watts of electricity when exposed to sunlight. Okay, so new solar panel, 220 watts this time. The design should ensure that more than 90% of these solar panels will generate at least 220 watts of electricity when exposed to sunlight. What is the smallest number of cells that a solar panel must contain in order to achieve this? Okay, so we want 220 watts, so then we've got to go, how many working cells is that? So if we go 220 divided by 4, we get 55. So that means, as a minimum, okay, our solar panel has to have 55 working cells. And so what we're going to do, the calculation we're going to perform then is we're going to say, all right, we've got between 55 and n cells. We're asked how many cells are we going to put in. Between 55 and n, out of n trials, and we know the probability of it being successful and it working is 0.91. So we have between 55 and n. And what we're going to do is we're going to keep changing n. All right, we're going to do a trial and error process here until the probability is larger than 90. So let's do that. And I think this is the best way to communicate it. So we can go n and then probability. And so let's just start, okay, and see how close we're getting to 90. So we're going to do the BCD calculation with 60 in there. So we do 71. BCD. 60. I'll know your BCD. So we've got 55 to 60 out of 60 and 0.91. And we've got 0.543. Okay, so what that means is if we have 60 cells in a solar panel, the probability that having 55 or more work is 0.543. So 60 is not enough. We're going to keep going until we just exceed 90%, because we want 90% of these solar panels to generate more than 220 watts, to have more than 55 working. All right, so let's go 65 then. And so all we're doing is just changing those numbers. Now, probably it's easiest in terms of syntax and typing it in your calculator. It'd be easiest to do this in the stat mode because you can change it very easily in there. So the lower boundary is 55, upper boundary is 65, 65, and 0.91. All right, so with 65, I've got 0.97. So that means let's just keep going down until we hit that number. So 65 is 0.97. Let's go to 63. All right, 63, I get 0.889. So that's not quite 90, so I need to check 64. And we get 0.941. All right, so what we notice here is when we have 64 cells, it's above 90% chance. When we have 63 cells, it's below a 90% chance. So this means if we want a solar panel that has 220 watts, that means at least 55 working, we need to have it have 64 cells. All right, so answer the question, therefore 64 are required. All right, good work. On to question 8. So here's our conjecture question. Consider the function below. The graph is shown there. All right. As x gets very large, what happens to the value of 4e to the minus 0.8x? What happens to the function? So all it's saying, right, is as x approaches infinity, I might have to scroll down to it. Okay, as x gets large, what happens to the function? And what we should be able to observe is that it's approaching 0. It's asymptotic to the x-axis. And so the way we will answer this is we will say the function, we can say f of x, or we can say 4e to the minus 0.8x, approaches 0. Okay, the function's getting close to 0. Now, that's perfectly suitable. Some people will add a bit more detail. Some people say it's approaching 0 from the positive direction. All right, we're not required to state that, just that it's approaching 0. It's getting smaller. Okay, part B, evaluate the definite integral from 0 to 4. So if we go from 0 to 4 of the function, we're just typing that straight into our calculator. Now, if you want, you can graph it as well, because we'll be referring to the graph a little bit. And if we evaluate this, we get 4.796. So it's a 3 sig fix, that's going to be 4.80. So the 6 rounds, the 9 rounds, so that gives me an 8. And then I've got my 0 there for 3 significant figures. Okay, fill in the table. Complete the table below. So we have A, 4, 6, 8. Here's the integral. We've evaluated this one already, so that's 4.80. And so then all we're doing is evaluating what's the integral from 0 to 6. And I've got 4.959. So I'll state both 4.959, which is 4.96. And we got what's the integral from 0 to 8? 4.992, which is 4.99. Okay, so we can start to anticipate there's some conjecture approaching here. You can even perform more if you want to. On the basis of your answers, make a conjecture about the value of the integral from 0 to a as a gets large. So what's going on for the integral from 0 to a of f of x as this number gets larger and larger and larger, and we can see it's approaching 5. Okay, that's going to be our conjecture. It's approaching 5. Sorry, not equals, approaching. Very good. All right, prove or disprove your conjecture. So, with a conjecture question, you can anticipate there will be one. What you need to do is, again, it starts with easy marks, all right? Starts with specific cases. Make sure we address the specific cases, and then we just take the proof as far as we can. So, if we're going to prove this conjecture is true, well, what we need to do is just manipulate this left-hand side. So we're going to form the integral from 0 to a of our function 4e to the minus 0.8x with regards to x. We're going to perform this function, this integral, as a gets large. So, all right, so we'll just keep it as is, we'll integrate. 4 is going to hang out. The integral of e to the minus 0.8x is 1 on top of minus 0.8, e to the minus 0.8x, and that's from 0 to a. Okay, so that's to say the integral of e to the kx is 1 on k, e to the kx. And we can simplify that, right? So again, use your calculator to help you, but 4 divided by 4 times 1 on minus 0.8, that's going to equal minus 5. So what we have here is we have minus 5e to the minus 0.8x. Now let's perform the fundamental theorem of calculus. We'll sub in the upper and the lower boundary. So it's going to be minus 5e to the minus 0.8a. Take away. So what we've got then, this term is minus 5e to the minus 0.8a. And I might even then, I'll leave it for now, and then this term becomes plus 5. Okay, so then we're going to focus on this part, and one way we could express that is like this. All right, so I've taken it to the bottom and made the power positive. All right, now as a approaches infinity, all right, as a gets large, e to the power of 0.8 also approaches infinity. So you can think, if I put the number 1000 there, what we have is we have e to the power, that evaluates 800. So we have e to the power of 800, which is 2.72 times 2.72 times 2.72 times 2.72. This number is getting enormous. Okay, so we have e to the power of 0.88. That's getting really large. And so then we have minus 5 divided by an incredibly large number. Okay, so this whole part, so this is approaching infinity, which means minus 5 on top of e to the 0.8a is approaching 0. All right, so that part's approaching 0. Therefore, the integral approaches 5. All right, so that's quite a different conjecture question insofar as we're talking about limits and things approaching certain values. But whenever you're asked to do something about that, just break it down into its parts. Okay, so here we're breaking down parts. We don't have to deal with that. That's a number. And then here we go. How can I express that in a way that sort of makes sense? We take that to the bottom with a positive power. We know that as a gets large, this number gets enormous. 5 divided by an enormous number is getting smaller and smaller and smaller. So this is approaching 0, and we're left with 5. All right, any questions? Okay, on to 9, we're making good time. All right, so again, this one's a little bit tricky as well. Consider the function minus x to the 3 plus 5x squared. For what values of x does the function equal 0? So this is it's 1 mark. You can just go straight to your calculator, you can g-solve those, you can find them via factorization, whatever's fastest for you. But we're asked to find when does this function equal 0? So what I would be thinking, factorizing it, and then applying the null factor law. Alright, so 2 answers, x is 0, x is 5. You can g-solve them from the graph. You can solve the polynomial. Those are our solutions. Okay, for the next one I'm going to say let's definitely refer to our calculator. We're asked, for what values of x is the function positive? So we know these are its roots. Okay, we have 0 and 5. And so we're asked, for what values is the function positive? When is this function positive? So I would just go straight to the calculator and graph it. Maybe I will bring up the graph actually. This might be a good place for us there. So the function is minus x to the 3 plus 5x squared. Okay, so we can see roots at 0 and roots at 5. Now we're asked, when is the function positive? When is the function above the x-axis? And so we can see it's positive for values less than 0 and between 0 and 5. Now we're not including those points because the function, we're asked when is the function positive? We're not asked about slope, we're not asked about things that would generally include the point. We're just saying when is the function itself positive, and it's for values less than 0, because at x is 0, the function is 0, and it's between 0 and 5. All right, for those values, the function exists above the x-axis. Okay, all right, so the reason we do that, remember, you don't do anything in vain. Here we have, for what values of x, for values of x for which it is defined, consider the function g of x, which is ln of some function. So the property we're drawing out here, and again, reasons to choose this exam and this question in particular, is ln of x exists provided x is positive. All right, so we have ln of minus x to the 3 plus 5x squared, and this is going to exist, this function exists, provided this function is positive. Okay, and so that's why we did that above. The ln function has asymptotes when this function is 0. All right, so on the axis below, sketch the graph. So I'll draw out a few things here for the graph. Graphs are 3 marks. Graphs are easy marks. Get your marks for the graph. All right, so I'm just going to put an ln in front of this and put some brackets around. Okay. So that's what our function looks like. So there's a couple of key things to think about here when you've got your graph. 90% of the time, they give you the V window. All right, so here they've given us a V window from minus 3 to positive 7 for X. We go from minus 5 to positive 5 for Y. So we've got that there. And we've asked to sketch the graph showing all key features. Mark and label the positions of its asymptotes. Okay. So mark and label the positions of the asymptotes. So we will sketch it. So I'll come up here. Here's my x-axis, here's my y-axis. Now we know from above, all right, the function is 0, at x is 0 and at x is 5. So that means our asymptotes are occurring at 0 and 5. So I might get a red marker. I think we're out of 0. So we've got an asymptote here, and the way we denote that, x is 0, and we have an asymptote here, x is 5. We can see that on the graph, okay? We can see those asymptotes occurring on the graph. Yep, so we've got those asymptotes, and now we're ready to sketch the function. So let's talk about how they're allocating marks here. Okay, they're allocating marks for the asymptotes. They're also allocating marks for its general shape. So for example, we've got a local max somewhere between 2 and 4. So on my calculator, I'd be G-solving that local max, saying where's that occurring? You know, unfortunately, there's also this click at 3.33. There's a local max. So I need 1, 2, 3, 4, 5. So 3.3 is here, and the height of it is 2.91. So I'll go 1, 2, 3. All right. So what they're doing when we mark it is we're looking to see that that maximum point exists in a box. Okay. So we, as markers, we set the boundaries of a box and say that point, that key feature of the graph, needs to occur in that box for you to get the marks for the turning point. Okay, we'll also look at things like the roots. Where are the roots occurring? All right, so the first root is 0.469, and the second root over here is 0.495. So this one's very close to 5, and this one's about half. Okay, so we're looking to see that they're in the right position, and it's asymptotic. We know it's asymptotic because as the closer it gets to 0, the more negative it's getting. 0.49, there it is. So that's 1, 2, 3. Good. Okay, so we've drawn that. We indicate it's asymptotic with the asymptotes and the arrows, showing it's going down and approaching it forever. And then the other side, we're only viewing it till we get to x is 3, minus 3. So I've been looking at that extremity, going when x is minus 3, what's the y value? And it's about, what, 4.27. So it's just above 4. So we've got x is minus 1, minus 2, minus 3. 1, 2, 3, 4. So it's about 4.27. It gets up to there. And it goes from here. And what's its root as well? Might be an important thing to consider. Its root is 0.42, minus 0.42. So that's minus 1, minus 0.42 is here. So it's doing this. Okay, so graphs, like all you're doing is copying what's on the calculator, but do it properly, all right? Talk about, again, easy marks to get. Graphing's an easy mark. Make sure you label the asymptotes. So that's quite a challenging graph to generate, okay? Most graphs tend to be a bit easier than that one. But this question draws out a few key features that I want to emphasize, all right? Logarithmic functions exist provided this inside is positive. If we have a 0 or a negative value in there, it doesn't exist, or we have an asymptote. Okay, move on. See part 1. Show that g dash of x is this. So the logarithmic function that we have ln of minus x to the 3 plus 5x squared. Now, whenever we differentiate ln of f of x, okay, so we'll write the rule up, ln of f of x, it goes to f dash of x on top of f of x. So that means our denominator is the inside, minus x to the 3 plus 5x squared. So here's y, dy on dx. And at the top we put the derivative. So when we differentiate minus x to the 3, minus 3x squared. When we differentiate 5x squared, 10x. Now the only thing they're looking for is that x is a common factor to both the numerator and denominator. We can pull it out the front. And then we can cancel the x, which leaves us with what they've got. All right, so a generous 2 marks there. Okay, hence find the x coordinate of the stationary point. Okay, the stationary point. So it's going to be stationary when the first derivative is 0. All right, stationary points occur when the slope is 0. Here we've found the derivative function. And it's even given to us, so even if you can't answer this part, you can still answer part 2, plus 5x. Okay, so this is a rational function, because it's a ratio. We have a numerator and a denominator. And rational functions, if we have a on b equals 0, it occurs when a is 0. So we only consider the numerator, right? The stationary points occur when minus 3x plus 10 equals 0, and we solve through the x. 10 on 3, 3.3 recurring. And we know there's only one stationary point. Like if we look at the graph here, there's only one maximum point where it's horizontal. And we found before that was x.33, 3.3. That's where we sketched it, right? 10 divided by 3, 3.3. Okay. Part D. Show that g of x has no points of inflection. So we can see from looking at it that it's concave down and concave down. All right, so it's not changing shape anywhere. So we're going to show that it doesn't have points of inflection. So let's make the argument as to why it doesn't have points of inflection. Now, points of inflection occur when h dash dash of x equals 0. Is the function h of x? Yes. G, sorry. When g of x equals 0, g dash dash of x equals 0, and sign diagram changes. So they're the two properties it has to satisfy. All right, what we will find is that it doesn't pass the first test. All right, the second derivative will never equal 0. So, a couple of parts to this. We've got the first derivative. It's this function here, minus 3x plus 10 on top of minus x squared plus 5x. And we need to find the second derivative. So all we're going to do is differentiate this function here. Okay, we have one function divided by another. We're going to use the quotient rule. So u is the top function, v is the denominator, and we'll smash all that together for the quotient rule. U dash v, take away u v dash, all on top of v squared. Alright, yep, so all we've done there, cranked through, found the second derivative. Alright, so let's expand the numerator and start to collect like terms at the top. And from now on, I'm going to disregard the denominator because I know point of inflection occurs when the second derivative is 0. This is a rational function, which means I'm only interested in the numerator. Point of inflection when the numerator equals 0. So let's expand the top here. We'll have 3x squared, take 15x. Over here, I'm going to leave that negative there for now, and I'll expand this quadratic. So we'll have what? Minus positive 6x squared, take 15x, take 20x plus 50. All right. And then we have here 3x squared, take 6x squared, minus 15, plus 15, take 20. And then take 50. So that's plus 2. Minus. Excellent, okay. So what we're required to do then is to show that this has no roots. It never equals 0, all right? Because points of inflection occur when the second derivative is 0. The second derivative is this on top of that. You know, it's a rational function. We're only interested in the numerator. So I think there's two ways. Probably your temptation would be first to jump straight to something like quadratic formula, and that's a perfectly acceptable way of showing it, okay? Because Probably the most concise way, however, would be to use the discriminant, which is part of the quadratic formula, right? So remember, quadratic formula, all right, this is the quadratic formula, and this part here is the discriminant. And if the discriminant is negative, okay, if the discriminant is negative, there are no solutions. All right, we can't square root a negative number, it has no real values. So all we're going to do is evaluate the discriminant of this quadratic here. Okay, so discriminant is b squared take 4ac. So in this circumstance, 20 squared and maybe 12 times 50, 600. All right. So what we'll say is because the discriminant is negative, this function has no roots, it has no solutions. All right, so how can we communicate that? Because delta is less than 0, h dash dash of x, sorry, g dash dash of x has no solutions, therefore no points of inflection. All right, so that's 6 marks. It's tough to get all of them out. But again, like we're trying to get as many marks as we can. So if we're asked, show that it has no points of inflection, what's the train of thought we should entertain? Points of inflection occur when the second derivative is 0. So you get marks just for finding the second derivative here. You're getting marks for collecting like terms. You're getting marks for recognizing it's a rational function. I just need to focus on the numerator. And then there, if you try and apply quadratic formula, you'll end up with the square root of a negative number, square root of negative 200, which means there's no solution. You demonstrate that it's true by quadratic formula. All right, so that's quite a tricky question. Let's go on to question 10. We have, consider the function below. 8 take e to the x plus 20 e to the minus x. All right, show that x equals ln 10 is a solution to this equation. All right, the equation that they give us is that it equals 0. So all we have to do is sub in x is ln 10 into this equation and show that it evaluates to 0. So we go, when x is 10, the left-hand side, ln of 10, the left-hand side is 8, take e to the 10, e to the ln 10, e to the ln 10, plus 20 e to the minus ln 10. All right, so all I've done there is substitute x is ln 10 in. Now, e to the ln 10, that simplifies to 10. However, this one here is a little bit trickier to show that it's a solution. What we have is we have 20 multiplied by, now we have e to the power of negative ln 10. There's a couple of ways to deal with it. I think the best way is to go 1 on top of e to the ln of positive 10. All right, and so then we've got e to the ln 10 in the denominator. And so what's this? This is minus 2 plus 20 times, we have 1 on top of e to the ln 10 simplifies to 10. 20 times 1 on 10 is 2, which is 0. So we process the left-hand side and we show that it is equal to the right-hand side. Now, anytime it says show that, that means really show it, okay? Don't skip any steps. Don't assume that the marker knows what's going on. Anytime there's a show that, you really have to demonstrate its truth. Okay, now we have another logarithmic question. Hence, determine the exact area bound by the graph, the x-axis and the y-axis. Give your answer in the form a plus b ln c. So this is another good logarithmic question. And we're asked to find, like if I sketch the graph quickly, this area here. All right, this is ln 10. We know that value is ln 10 because it's the x value that makes the function equal to 0. We want this area here. So the integral that we're performing then is the integral from 0 to ln 10 of the function, which is 8 take e to the x plus 20 e to the minus x. All right, now straight away we can integrate all of these terms. Integral of 8 is 8x. Integral of minus e to the x is minus e to the x. This becomes 20 e to the minus x, the negative, okay? And that's from 0 to ln 10. All right. Next, we just sub in lower and upper boundaries, applying that fundamental theorem of calculus. When you're doing fundamental theorem of calculus, just sub in lower and upper boundaries, and then let's deal with it after. So we've got to collect like terms where they've gotten a way they want us to express the answer. Okay, so 8 ln 10, that can stay as is for now. Minus e to the ln 10 simplifies to minus 10. Now we know e to the minus ln 10, we did that before, that simplifies to 2. Sorry, that whole term simplifies to 2, doesn't it? All right, let's not skip ahead, I'm probably trying to get a bit ahead of myself. E to the minus ln 10, that's 1 on top of e to the ln 10. Okay, so that's our left bracket. Over here, take away, that's minus 1, and that's going to be minus 20. All right, so e to the 0 simplifies to 1. Okay, now let's try simplify this a little bit. 8 ln 10, take 10, now that's going to be 2, because that simplifies to 10, 20 divided by 10 is 2, and then we have take minus 21. So what are we left? 8 ln 10, take 12 plus 21. Take 12 plus 21, 8 ln 10 plus the number. All right, so this is another one where if you type this into your calculator and you type this in, you can verify you've got the correct answer. Very good. Okay, turn the page, we've got 2 to go. Okay, we have an integration question. We're presented with areas. So consider the graph of f of x, that's the dashed line, and the graph of g of x, which is the solid line shown below. 2 functions meet when x is 1 and x is 2. The enclosing regions marked B and C. The region between the graph f of x and the x-axis from x is 0 to x is 1 is marked A. So they're just describing what they've marked each region. Integral from 0 to 1 of f of x is minus 0.33. Integral from 0 to 2 of g of x is 0.05. All right, I might give it a quick sketch. So have a read of that information there, comprehend that, and I'll do a quick sketch up here. I'll read. We have A, B, C, D. All right. X is 1, X is 2. Okay, find the area of region A. All right, so we know the dotted blue function here, that's my f of x, and the red function is g of x. All right, and we're told, the first point we're told, the following information is known, is the integral from 0 to 1 of f of x is minus 0.33, okay? So the integral from 0 to 1 of the blue function is minus 0.33. It's negative because it's below the x-axis. So what's the area of region A? The answer is 0.33. Area is a positive measure. So for A, 0.33. All right, part B. Find the integral from 0 to 1 of g of x. Okay, so just over this region here, g of x Now, we're not asked to calculate an area, we're asked to evaluate the value of an integral. And because it's below the x-axis, our answer is going to be negative. All right, so again, the difference between area and a definite integral. So evaluate the integral from 0 to 1 of g of x. So that's asking for this whole area here, right? The area of a and b together, but it's negative because it's below the x-axis. So we know a is 0.33, and we're told the value of area b. Area b is 0.45. And so the definite integral evaluates to minus 0.78. Okay. Show that the integral from 1 to 2 of g of x equals 0.83. All right, show that this is true. So let's break it down into parts. All right, so we're interested in this area here, C plus D. That's what we want. We want the area of C plus D. Now I think we're told area C is 0.69. All right, so we know that part, but we don't know D. We're asked to show that together they add up. All right, so what we do know, however, one of the last things we're told is the integral from 0 to 2 of g of x. That's the second point, sorry, the integral from 0 to 2 of g of x. We do know what that is, okay? That is 0.05. All right, that's our second point. And we know the integral from 0 to 2 of g of x is equal to the integral from 0 to 1 of g of x plus the integral from 1 to 2 of g of x. Okay, so we can break up the integral. Now we know, so we're told that that's true. We know this value because we just evaluated it. The integral from 0 to 1 of g of x is minus 0.78. So we have minus 0.78 here, and then plus integral from 1 to 2 of g of x. And if we rearrange this equation, we're going to plus 0.78 to both sides. We get 0.83 equals the integral from 1 to 2. Okay? So what do we do there? We know this value, we know this value, so then we can localize that one by moving that over to the other side. It's just like an equation, that's our unknown, and so the integral from 1 to 2 of g of x is 0.83. Okay, hence find the integral from 0 to 2 of f of x. So the integral from 0 to 2 of f of x is going to be minus 0.33 plus the area of d. So we need to go, well, what's the area of d? Well, we can find d because we know the integral from 1 to 2 of g of x. We know that that is 0.83, right? So the area under the red function is 0.83, and we know region C is 0.69, okay? So that's equal to C plus D. We know region C is 0.69, so we can solve for D, and we get D is 0.14. So we have the value of D, now we can answer the question, what's the integral from 0 to 2 of f of x? Okay, 0 to 2 of f of x is minus a plus d. Area d is positive because it's above the x-axis, so we have minus 0.33 plus 0.14, and what's that take us to? 2019. Negative 0.19, sorry, because that's negative. No, because if we look at the past three, all of the past three are definite integrals. So they're not area questions. Only when it's area will we put units squared, and only when it's area do we have to make it sure it's positive. Yeah, good question. Just in A we need units squared, yeah. So in A we should technically have 0.33 units squared. Yeah. Okay, last one. All right, so this is a question 12 here. This is a good example of a question about comprehension. And they tend to do this with stats questions, and what they do is they overwhelm you with information. This isn't something like nodes and edges and so forth. It's not something that's part of the methods course, but it's something that they introduce to you in the exam for you to read, comprehend, and then answer questions about. So one of the skills they assess is comprehension. So let's have a read of it. Again, it's getting late in the exam, right? We don't want to rush over it. We want to make sure we answer everything properly. All right. Networks are a form of mathematical model used in modelling the connections between people. A diagram of a network is shown below. The circles are called nodes and represent people. The lines are called edges and represent connections between people. Node degree is an important measurement in a network. Node degree measures the number of edges that connect to a node. The black node marks A in the diagram, so we can look at the diagram presented to us. There's a black node, and it has 3 other connections to it. You can see it's got 3 lines connected to other nodes. Let the random variable x represent the node degree of each node in a network. For the network above, the distribution of x is shown in the histogram below. All right, so we have a distribution, and it's very heavily skewed to one side. So, what does the histogram on page 22 tell us about the nodes in this network? Okay, so we're looking at the histogram, and it has this shape, doesn't it? It's very heavily skewed in this direction. All right, does anyone know the name of that skew? I looked up a simple way to remember it yesterday because I always get them confused. And this is a positive skew because that tail is pointing in the positive direction. Okay, negative skew, tail points in the negative direction. So we have a positive skew here. All right, so that's the first thing. That's a way we can describe the shape of the distribution. The distribution has a positive skew. And skewness, right, like it goes on to describe the relationship between mean and median. That's not so relevant right now. So what we're going to say is that it's positively skewed. And so what it means is that most nodes only have a few connections. Most nodes have a few connections. All right, and a small amount of nodes have many. Okay, so if we look at the distribution, I'll bring it up on the computer screen. Okay, so most nodes, all right, occur between 0 and 2. There's a few between 2 and 4, and you look, there's not many nodes that have 8 to 10 edges, right? Okay, so all we're saying is most nodes have a few connections and a small amount have many connections. All right, here we go. Random samples of 50 nodes are taken from the network. Each node, the value of x was recorded, and the sample mean, x bar 50, was calculated. So that's 50 observations of x are produced, and it gives us the distribution shown below. Which feature of this histogram suggests that x50 can be modelled by a normal distribution? It is a bell-shaped curve. It follows a normal distribution. It is bell-shaped like the normal distribution. So our answer to part B is just the word bell-shaped. Word is bell-shaped. Okay. The distribution has a mean of 2.644 and a standard deviation of 2.106. Determine the mean and standard deviation of x50. So here we're at continuous random variables, okay? The mean of x50 is equal to the mean of x, all right? So the mean of x will always trump the mean of xn if we're told the mean of x. And we're told x has a mean of 2.644. The standard deviation of x50, however, is equal to the standard deviation of x divided by the square root of n. So in this circumstance, we have 2.106 divided by the square root of 50. And I would just leave it like that, rather than stating it's a 3 sig fix. That's going to give us the exact answer. Okay, so that's the mean and standard deviation of x50. All right, turn the page. We have the nodes in the network on page 22 and 23 describe a community of mathematicians. Mathematicians collaborate with each other by working together and jointly publishing papers about their work. Edges between any two nodes in the network is like Jeff Slattery's folio, just all the nodes is connected. The edges between any two nodes in the network indicate that those two mathematicians have collaborated. One university believes that in general, its mathematicians collaborate more than those in the community of mathematicians. A sample of 50 mathematicians from the university is taken. The average number of mathematicians with whom they have collaborated is 3.5. Okay. So it's talking about connections. One uni is saying they're more connected than another because they have an average of 3.5. Find the probability of obtaining a value of x50 that's equal to 3.5 or greater when taking a random sample of a size 50 from the network. All right, so what we're asked here, what's the probability of x50 being larger than 3.5? So we have the mean of x50, we have the standard deviation of x50. This is an NCD calculation, right? So from 3.5 to infinity, and then we go standard deviation and our mean. And we evaluate that. So normal distribution calculation. Okay, does your answer support the university's belief? Okay, it sort of does. We can say yes, because, all right, what this probability calculation presents, I'm going to describe it and then I'll write an answer. I'm going to describe it and then write an answer. All right, the probability of randomly selecting 50 mathematicians and them having an average of 3.5 or more collaborators is 0.113. The university says its average is 3.5. Okay, so it's quite low from that happening randomly. It would seem the university is more connected. So let's try and articulate that somehow. Let's say yes. Okay, so always break it down. Answer the question, then justification. And maybe I'll write it up so then you can see. So yes, and the probability, we can say from part D. Of Now, this is where there's room for a little bit of interpretation in all of statistics. So it's not that saying yes is the correct answer, because you could argue, like, whilst this probability is low, it's not impossible. Okay, it's not impossible. It's not an impossible probability to occur. So you could say, while it might seem that way, it doesn't guarantee that the university collaborates more. It just seems, based off the probability calculation, that they do. Excellent. All right, so that takes us to the end. So if if you're working through the exam there, what's that, 90, we're going to go for 1 hour 43, so you have 27 minutes left to go through and check. So that's where you